Hi, welcome to video 3.4. In this video, we'll be covering the charges of complete polypeptide chains, which are very common high-level questions that are difficult for midterms in biochemistry when protein is on the topic. A quick word of warning that being able to do these questions does require that you know the pKa's and the structures of the ionizable amino acids. You also need to know which ones are not ionizable. There is truly just nothing that can replace memorizing these amino acids and their structures, but when it comes to actually applying it, I'll hopefully give you a bunch of tips in this video. As a reminder, for acids and bases, there is an HA form and an AA plus form. So we can have the case of neutral acids. So for example, good cases here include the carboxylic acid. Right, we see this carboxylic acid functional group in many different places. We see it in the C-terminus. We see it on glutamate. We see it on aspartate. Right? All of these cases, we see carboxylic acids. So that's one example, where the HA form turns into the A- form. Right? The A form, therefore, has a negative charge, and the HA form is neutral. The important takeaway here is that you can't just memorize and say, oh, if there's no hydrogen, if it's A, it has to be negative, because there's also the case of the positive acid. Right? Nitrogens are very common traps here. So for example, if we see NH2s, we see this on the N-terminus. We see this on lysine. And we kind of see this on arginine. It's a little bit different, but same principle. Right? And I'm trying to think if there are any other amino acids that have a free NH2. Well, if they are, I'll remember them after this video. But regardless, in these situations, right, HA plus means that when we have the actual NH3 plus, we take away a hydrogen from it. The form that's missing the hydrogen, which we would call A, is actually neutral. The HA form is the one with a positive charge. In this case, if the amount of hydrogen is low and the A form dominates, that doesn't mean that we have a negative charge like it did up here. It means we have no charge. On the contrary, if the amount of hydrogen is high, if the pH is low, right, that means high hydrogen, the HA form would dominate in both cases. For this, carboxylic acid, that means no charge, but for the nitrogen, it means positive. So, with that in mind, let's do a couple practice examples of questions that involve this material. So, for the first question, feel free to pause the video and take a stab at this. It asks, what is the overall charge of this four amino acid peptide: alanine, glutamate, asparagine, and lysine at pH 7, pH 1, and pH 14. To solve this, I want to first remember that there's always an N-terminus and a C-terminus. And I like to make little tables like this. Right? We'll start with pH 7, and the idea is to go one by one and figure out what the charge is going to be. It can be very helpful to note any pKa's that are relevant. Right? So the N-terminus, we'll say, is around 10, the C-terminus around 4, lysine around 10.5, and glutamate, right, was around 4 or 3, whatever the number you want to choose is. We'll just say 3. Right? These numbers are going to help us. We don't necessarily know what they mean yet. It depends on the pH. So with pH 7, let's go through. The N-terminus could be ionizable. So if we think about this, the pH is low. It's lower than 10, which means that the N-terminus is going to favor the HA form. Right? There's more hydrogen around since the pH is low. HA form dominates, and for the N-terminus, that means there's a positive charge. Alanine is never going to have a charge. Same with asparagine. Right? It's important to recognize that those neutral, amino acids that are not ionizable, they're never going to give you a charge, so you can ignore them. Now, for glutamate, at a pKa of 3, right? Remember with glutamate that it's going to be negative or neutral. Because it's a carboxylic acid, right? So below pH 3, we'll have the acid. Above pH 3, we'll have the negative charge. pH 7 is higher. Again, that means less hydrogen. That A form dominates. So we're going to have a negative charge. And for lysine, Again, in a sense, we don't have to do this rigmarole because we know that lysine is always positive at pH 7. That's how we memorized it. To understand the rigmarole, though, pH 7 is lower than 10.5, more hydrogen, so we dominate. That nitrogen is going to be positive and protonated. The C-terminus is negative, and we get an overall charge of 0. If you had trouble before and you want to try it now with pH 1 and 14, feel free to pause the video. I'll go through them fairly quickly. At pH 1, that means that there's a ton of hydrogen. It's very acidic. Anything that can have a hydrogen will have a hydrogen. For the N-terminus, that means it's positive. For the glutamate, that means it's neutral. There's no charge, right? We're going to have, since it's below pH 3, right? If we want to use this idea again, pH 1 is less than pKa of 3, means there's lots of hydrogen, so now the HA form will dominate, which doesn't carry a charge. Lysine will remain positive, and the C-terminus will also become neutral, meaning that now the overall charge is +2. It's worth noting that in acidic conditions, you expect the charge to go up. You expect positive charge, I should say. Right? Moving to pH 14, now the pH is so high, there's very little hydrogen, so the A form is always going to dominate. For the N-terminus, that means that we're now going to be neutral. For the glutamate, that means that we'll remain negative. Right? We still have very little hydrogen, so this A form dominates. And for the lysine, now we've hit 10.5, we're also going to be neutral. For the C-terminus, we remain negative, and overall the negative charge is -2. Great, so that's how we can get the overall charge of the entire polypeptide. Now there is one important trap that I want to warn you of. A common trap is asking what is the charge of the alanine at pH 7? Now keep in mind, the way that I like to approach these problems is to view the N-terminus and C-terminus as separate things. But truly, the N-terminus is not an amino acid, it belongs to the alanine. And likewise, the C-terminus is the C-terminus of the lysine. So if I ask you for the charge of glutamate that's in the middle, it doesn't have a free N or C-terminus attached to it. It's in the middle. It's a residue of this protein. Its charge will always just be the charge of the R group. But if I ask you specifically about alanine, at pH 7, its charge is actually +1. Right? So, or I shouldn't say +1, right? The overall charge of this alanine, is +1. Because free alanine, right, would be neutral. Free alanine has both the positive N and the negative O. So it would be neutral. But in this case, the alanine only has its N-terminus. The C-terminus continues on and produces the rest of this protein. So if we ask what is the charge of just the alanine, the answer is +1. Be careful when questions are worded this way, right? It's one thing to ask about the charge of alanine by itself, and it's another to ask what is the charge of this alanine in this sequence. With that trap out of the way, there's a much bigger example. To save time in the video, I'm going to go ahead and just reveal the answer shortly. So go ahead and pause the video and try to solve this problem. All right, let's go through, much less explanation, just to make, I'm not going to write an epic here. But at pH 7, we expect everything to be as normal. So the N-terminus is positive, histidine, right? At pH 7, if we think about it with its pKa of 6, that means that the pH is high, there's not enough hydrogen, so it will be neutral. But it'll be positive at lower pHs. Right? The N-terminus will be neutral when it's basic, when the hydrogens are taken away from it, but positive otherwise. Right? When it's acidic, it has lots of hydrogen. Cysteine at pH, I'll go through here. So neutral, tyrosine neutral, tryptophan neutral. At pH 7, the only things that are going to have charge are your charged ones, arginine. Right? But here we didn't see any lysine or glutamate or other things that would be positively charged. The C-terminus is going to be negatively charged at pH 7, giving you an overall charge of +1. For pH 1, now anything that can have a hydrogen will. Cysteine remains neutral. Tyrosine remains neutral. All of these remain neutral. Arginine is finally, oh, actually, no, it's going to have its hydrogen, so it's positive. Aspartate is neutral. Glycine is neutral. The C-terminus will have its hydrogen, so it will be neutral as well. The overall charge now is +4. And for a pH of 14, again, we have neutral, neutral, neutral. So all the hydrogens are now taken away. The A form dominates. That makes cysteine negative. That makes tyrosine negative. That doesn't touch tryptophan or valine or isoleucine. Arginine now becomes neutral. Aspartate not affected. Glycine not affected. C-terminal remains negative. With this in mind, our overall charge is now -3. So hopefully this was something you could do on yourself, and you can see now how knowing the pKa's and relating them to pH to think about which form dominates is a great strategy here. Now, this is going to be an optional, so if you at the 200 level, you probably don't need to know this, but I do want to cover this here, is that while there are tons of different things that can be asked about pKa and charge, in biological systems, extreme pH is pretty rare. There's only really 2 amino acids, or 1 amino acid that really matters here. Now, for amino acids like tyrosine, where the pKa is 10.5, and it's neutral at pH 7, it's mostly going to be neutral, right? The pH has to get very high to start seeing this, so high that, of course, it would kill cells. But when the pKa is near 7, things get interesting. So with histidine, its pKa is 6, meaning that once we're at pH 6, there's going to be 50-50 mixture of these, right? So that because, again, when pH equals pKa from the Henderson-Hasselbalch equation, HA must be equal to A in terms of concentration. So if I had 100 molecules of histidine at pH 6, 50 of them would be like this, and 50 would be like this. So here's an interesting question. At pH 7, if I have 100 molecules of histidine, are any of them positively charged? Right? Because that's important in terms of the structure of proteins that have histidine in them. Because pH 7 is realistic biology, right? For a question, I would say it's mostly neutral, but recall this equation, right? Big takeaway is that if the pH is equal to the pKa, the concentration of A and HA are equal. So we can actually rearrange this. If I know the pH is 7 and the pKa is 6, I take the log of the two values. Here I put His over His positive because it's A over HA, and the HA form of histidine is positive. Therefore, the log of His over His plus is 1, and you can basically solve, right, 100 molecules of histidine. So I just did some quick math here. I'm not going to take you through it too much, but you can do some math to basically calculate how many His plus molecules do you have, and the answer is, on average, about 9 of them. So even at pH 7, histidine has a bit of a positive charge, right? 9 of its molecules out of 100, or 9% of its molecules, are positive. This will be important when we start talking about protein function in Chapter 4. Anyway, now we've done the charge of large polypeptides, so it's time to take a step back and go really back into structure. We'll talk about the secondary structure of protein in the coming videos. I'll see you there.